Good morning, dear Vice President, dear Minister, dear members of the European Parliament and the European Commission, dear colleagues. It is my pleasure here to open the presentation of the FET Flagship by reporting on the progress we made with the Guardian Angel for a Smarter Life project. And I will start by acknowledging the team effort of the consortium, a very complex consortium that we built, made of industry, research institute, universities. And I will also acknowledge the great collaboration we have between EPF Lausanne and ETH Zurich, represented here by Professor Christopher Herold. In my outline, I will talk essentially about two key things. First, autonomous smart system and their future, and how the future of such system and their implementation can impact the society and the economy. And second, about zero power technology as enabler of this autonomous smart system. And I will show you the progress we made in building roadmaps where the scientific and technology challenges as placed as high priorities. And as a result of the work we did during the last year, we are today able to show you how this system can impact and create new scenarios of prevention on energy efficient type of system and how this is mirrored in different domains of our lives. Very important, how we govern this project, a complex partnership, and how we place our work in the international context. And in order to start this technical presentation, I have a short movie that is summarizing our vision.
Today, our well-being is our most precious resource. Guardian Angels is a network of quasi-invisible nanosensors that monitor information about you and your surroundings. Tiny autonomous smart systems that integrate into our lives. Small but powerful, advanced nanoprocessors compute parameters such as heart rate and fatigue levels. On the quest for zero-energy electronics, Guardian Angel sensors harvest power from the environment using solar energy, piezoelectric currents created by vibrations and movement. Even energy out of thin air from changes in temperature and electromagnetic charges. Information is communicated among microprocessors as well as through smart devices and stored using cloud computing technology according to the strictest privacy standards. Integrated into our clothing, this non-invasive technology can alert us when we are dehydrated or when pollen is in the air. Guardian Angels use cutting-edge technology like flexible electronics in the latest materials to bring advanced science to everyday life. Simple, affordable and intuitive, they protect the most fragile among us, communicating what a child cannot tell her parents. Guardian Angels accompany us throughout our life and bring more autonomy to seniors by communicating information about their health to caregivers. Embedded in everyday objects such as cars, interconnected Guardian Angels communicate with traffic, pedestrians and your vehicle to reduce accidents. Emotional feedback frees us up to concentrate on what is important and helps professionals to stay focused in critical situations. Nature can be hostile and unpredictable. Zero-energy networks and ad hoc communication systems use autonomous robots to guide us away from danger before situations become unsafe. The next generation of communication systems will improve safety, prevention, and assist rescue missions. We are already connected in so many ways, but those with Alzheimer's, for example, are still helpless when disoriented. Guardian Angels can help. Assisting those with extremely limited mobility, research on brain-machine interfaces promises to open new worlds of movement and interaction. For Guardian Angels to become a reality, European universities, research centres and Europe's high-tech industry have joined forces. By investing in the future of everyday technology, Europe will affirm its scientific leadership by bringing discrete, zero-energy devices to all. Guardian Angels. for a smarter life.
So, as you might see, this project is directly contributing to the future of information and communication technologies by placing the main focus on the distributed intelligence, which is a key part of the information revolution. We are bridging, in fact, nanotech, computer advances, and distributed intelligence in order to generate new type of application and new technologies to support this application by what we call the zero power technology. Where this type of technology will be placed and where we focus our effort. And on these slides, you have here depicted what we call the application placed at the edge of the cloud. But what is after these technologies? And you see there a lot of new technologies and applications that are practically embedded in everyday object. They are practically invisible from the user, and they have a various type of application in monitoring patterns, like the electronic skin is one of our roadmap for monitoring biological signals, can have application in hospital, can reduce the impact and the can improve the monitoring of the person. You have new progress that can be enabled by this zero power technology on human-machine interfaces. You have seen in the movie this idea of supporting people in an extreme condition, in under stress condition, by taking appropriate action, advising people into that. You can have connected to this type of application new generation of smart drive assistants that are helping all people to drive under increased safety and security condition, and many other applications in health and fitness. But there are other classes of application that are indirect from this project, like environmental monitoring and enabling with the needed technology the autonomous cooperative robots. Now, the definition that we propose for the Guardian Angel as a zero power smart system is practically system that features sensing, computation, and communication together with energy harvesting, enabling what we call beyond human aptitudes. And in order to make this happening, we are concentrating practically on 4 key technologies. The first one is ultra low power computing, where we are looking at the limit of computation in terms of energy efficiency. You might know that computation is practically the technology that experienced the highest progress. We see it in our lives today, but it was a quest for high performance, not necessarily for high energy efficiency. So we are looking on candidates that can reduce the consumption and take advantage of such high efficiency in the way we compute the information bit today, and reaching factors of gain of up to 1,000. Same in communication. You will see that we can here gain order of magnitude, 2 to 3 orders of magnitude practically in communication, make them more efficient if we design our communication according to the specification of a particular system. Same in sensing, where we can take benefit of new nanotechnology, of new generation of principal and sensor with the readout electronics to reduce the power. And not last, energy harvesting. Today we are powering our system with batteries. Tomorrow we can harvest the energy in the environment, store this energy locally, do the power management and power up our system. But this combination between harvester and this energy efficient technology will create what we call the zero power platform. And this is the core of our project, creating these 3 components of the zero power platform: the energy efficient technology, the harvesting, storage, and green batteries, and the design with such very complex technologies in a heterogeneous way. And we believe this will be a generator of innovation and a new application, not only the one that we propose here in the project, but there are unexpected applications that will be created. And this will be an open platform for Europe, not only for the partners that are in the project, but also for the SMEs of Europe, also for creating startup, creating innovation. And we see here the evolution of this platform driven by the 3 type of generation of Guardian Angel that we have: the physical one, the environmental, and the emotional Guardian Angel, and I'll explain you later on. So the key component, the key node of a guardian angel stands for this idea of a body area network, right? It's practically we are talking about a system that includes all the components that I was telling before, and they can take advantage of miniaturization and embed that in few millimeter cube. Today, a processor volume, the processor that you have in your computer is few millimeter cube or less. So this is the size of a mosquito, right? So it's an extremely tiny amount, but it consumes a lot of power, tens of watts. What we want to do is to have such a system in the future consuming hundreds of microwatts. And this will enable amazing type of application. In order to do that, we have to make the right choices of the technologies, of the design, of the software that we put in such a system. And this needs what we call heterogeneous integration. And in order to maximize the effort, the impact of a heterogeneous integrated system, it should be provided to the society at an affordable cost. So we plan to build our project on the solid science, engineering, and economics that already exist in Europe, on domains where Europe has leadership. And this is not making single choices in terms of technologies. We believe that each material, device, and scale should be used for its best performance. You will find in our project the use of silicon, the use of carbon materials like graphene and carbon nanotubes, 3-5 material, each of them selected and proposed to be used there where it delivers the best performance with the highest energy efficiency. And the drivers are indeed the power consumption, novel functionality, and 3D integration of such system, hybridization of 3D with other type of approaches, or system on foil could be solution depending on the application. We built during this period very particular roadmap for the future. And the difference of this roadmap compared to all our roadmap that you find in this domain, in industry or in other program funded by EC, is that we combine a top-down with a bottom-up approach. These are not roadmaps where we are looking just what's the future of a certain technology in computation, communication, sensing, and so on, and how we can improve that. We look from the system perspective. We have selected certain classes of application in the physical GA, monitoring the body, biological signal, environmental GA, where you look into having access of an augmented reality signal you cannot sense in your environment, pollution, allergens, radiation, and so on. We look at the human-machine interfaces in the emotional GA, how the body reacts to emotion, and we try to see where autonomous system can make the difference in application and what are the technology requirements of this application. And then we came and narrowed down the option in each of the layers that you see here to build the roadmaps. And I have here an example. It's extremely technical, but what this slide is telling you is, for instance, in computation, that we have two types of options. We have short-term option to deliver system in a time frame of 3 years to show, to report to the funding agency what we can achieve with this system, and then we have long-term looking type of approaches and selected type of technology that can, in 7 or 10 years, deliver better performance, but need a more advanced type of research. And the metrics that we apply are system-level metrics, are not only device-level metrics. Same, we look in the communication roadmap. We compare today what are the immature technology that we are using in our mobile devices and other type of communication, and where are the limits of communication in the future. And we analyze communication in between nodes of our system and in between nodes of a central system. And we look at metrics that are very fundamental and are very little explored today, like the energy per useful communicated bit. It means you have to consider the transmitter, the channel, and the receiver, and we come with ideas for pushing by 2-3 orders of magnitude down the consumption, which is 1,000 less that state-of-the-art devices, communicating a bit of information, a 2 meter with 10 picojoule or 100 meter with 10 picojoule. Such approach cannot be successful if you do not integrate all the levels needed from technology up to the system, algorithms, access technologies, all together. This is the added value of the flagship. These are not small projects focusing on different domains, but this is a federative approach when we put together all these domains. All our roadmaps have been built like that. Same in sensing, very important. We look at started for a fundamental limit, which is the minimum power to read a noisy signal at the thermal limit, and how this power is correlated with the resolution you need in sensor. And we came with this fundamental limit of the order of 100 of nanowatts, and then we start to build and to propose solution for all the type of sensor that are needed in the application that I mentioned. And we have very detailed roadmap. This is a result of 1 year of work in all the type of measurement of body activity, of biological signal, readout circuitry. So these are new roadmaps that you will not find in any other industrial type of approaches. Energy harvesting is a very ambitious and important part of the project. And the harvester we propose, they are harvesters that should operate in dynamic, real-life type of condition. It means they should be built with multiple harvesting interfaces, with the associated storage of energy and power management. And what you should consider in this case, let's take just the solar or light energy type of harvester, is that this type of harvester, it's on a wearable system, should operate indoor and outdoor. And the technology we have today are optimized for particular scenarios, and here you need to make trade-off and have the best technology that is delivering the necessary power. So there is a lot of work in order to reach the target, but we make our choices and we have solution for that. The application that we foresee are really focused on this domain: health and prevention, safety and work and driving, and energy efficiency. So this is the result of a high interaction with Technology Transfer Institute and with industry in Europe. We have a first family of GA system that what we call physical GA family. These are small, non-invasive systems that are proposed to be used for monitoring of physical and physiological parameters in humans. And we have selected two main classes that we think they will have the highest impact on the society. First is the monitoring of frailty and status of elderly. This is about having an objective assessment of frailty process using early markers. And we discuss with the medical community what they do not have is long-term measurement, continuous measurement, structured data that can assess frailty. Same for the early diagnosis of and management of metabolic diseases like diabetes. This type of diseases demand a high cost in the medical care. If you can do more in prevention by a multiple physiological type of monitoring, as mentioned here, you can detect them in a very early stage, and by detecting kind of complex pattern, and you can change the way we invest in the medical cost and health cost today. In environmental GA family, we are working with big European companies like Siemens, and here we propose application that standard the interface between people and their environment, providing relevant and real-time type of information. We have a project to build a smarter quality companion for indoor and indoor that you can have it with you in your mobile phone or in your wearable system, which is an artificial sixth sense type of system. And we have a system that will be planned for disaster management. We see that in the world there are many places where disaster management is crucial, and such a system, when you identify environmental risk, but you can also use it in order to take real-time action or make real-time analysis of water or whatever air, is very, very important. Last but not least, the emotional GA family. This triggers a lot of reaction. How we here reading interaction with emotion of people? Are you entering into the privacy of the people? And let me again define here what we mean by this family. It's really about sensing the body's reaction to one emotion or state of the mind correlated with environment and context to provide an objective and holistic information in order to deliver improved services. How do we react? How can we improve our reaction to this extreme solution? And here we are looking at two classes of major application. First, enhancing the emotional performance or well-being of healthy people that are exposed to such situation, when you take into account the stress, the tension, the fatigue level, and you provide advice or action to increase the people's experience when performing a task. And second is about supporting patients, and here it's about human-machine interfaces. Here we are interacting practically in different domains with the patients, so we are evaluating the effect of various treatment to create personalized treatment or practically detecting the efficacy of this. We are monitoring practically again, the efficacy of such drugs that they deliver like psychiatric drugs to patients, and we have an approach for pain therapy. So we have selected practically application in healthcare where we are delaying the onset and decrease the severity of the diseases. And we believe that this will have a significant improvement in quality of life, reduction of hospitalization, and reduction of cost. And our key to domain, again, metabolic diseases with diabetics in the core of the focus of our smart system. Diabetes is a major health concern, touching more than 300 million people with huge cost. And second, it's about aging population, frailty and aging population. And it was just cited in the opening of one of the ministers before that by 2050 we'll have more than 25 people over 65 in Europe. We did more detailed things than that, and I have no time to discuss about this. We assess this type of demonstrator that we support by our technology in terms of impact on science, economy, society, and innovation. And innovation, it's a very, very important criteria. And we took into account, we have practically committees that are working on the ethical aspect, data security, in storing and in communicated data with solution at hardware and software level, and the very early involvement of the end user to assess the system and have feedback from them and have great ideas sometimes from the end user. And why this GA flagship is so unique and can do more that you can do with the funding associated to smaller projects is unique because if you are looking at the value chain of the semiconductor business, this is a unique project I know funded by European bodies that will include practically all the levels of the value chain, starting from new materials, new technologies to advanced characterization, modeling, system integration, and system validation. And this cannot be done otherwise than in a time frame of 10 years and with a significant funding. And what will then happen is that we'll generate practically a lot of impact, not only in terms of object and technology, but new services in health, aging society, intelligent transportation. You see the increased area triangle that we have here. The budget that we have for this will be practically distributed between the system application and the technology platform. The zero power technology platform will have here practically 60% of the budget, 600 million, and we have roughly 300 million going into the demonstrator we want to show. We are putting in place a principle of corporate governance applied to a non-profit organization, a professional one having a scientific steering board and an executive level, a board of directors, and we have a unique approach for innovation. We'll boost innovation, we'll fund innovation creation of startup and access to SME to our platform. As of today, the consortium is made of 60 partners, 27 universities, 14 industrial companies, and 90 research organizations from 16 European countries. This is a result of 2 open calls that we launched during the 1 year, where we have 76 applicants and 32 partners. We have 3 major cooperative actions that are at international level. One with One Mind for Research in US between engineering and medical community. Second one in US with the Energy Efficient Electronic Science Center that is practically including the major 3 universities in US, Berkeley, MIT, and Stanford, and one with Japan, with Tokyo Tech, Nissan, and Toshiba for future zero power technology and new classes of application. And with that, I will close my presentation by trying to make this parallel thinking. Is 1,000 times more efficient smart sensory system an ambitious and visionary system? What does it mean? Just think that this will correspond to drive a car with few milliliters of gasoline on 100 kilometers. We need this type of energy efficient technology in the future. Thank you.